Today we're going to be using the analysis that we did in the last video on voltage divider circuits to give us a unified approach to look at a wide variety of analog sensors. Now this approach is not only flexible for different types of sensors, the concepts we're talking about work for both CircuitPython and Arduino. We're going to focus on CircuitPython for this video. However, just to get things started, we're going to look at the case of a flex sensor with Arduino first, and then compare it to CircuitPython before we continue to move on. So this program is divided into three sections. Up top, we have our variable declarations. If we're using any libraries, we would have those up here as well. Essentially, we are saying that we're going to have a variable called sensor pin or pin value. We're telling the system what type of value it's going to be. So in this case, these are integers, so we're telling it it's going to be an int. We're also going to be telling it, for example, that we're going to have voltage levels. Those are decimals, and so we're telling it that it's a float. So in C, you have to declare a variable, which means you announce what type of variable it is before you use it. That's not the case in CircuitPython. And then it's usually a good idea to initialize it, which is, again, just to give it some initial value. The next two steps are shared between all Arduino programs. So the first is a setup function, and this runs when you power the device on. And these are things that you just want to do once at the beginning of a program, rather than something that you would keep doing over and over again. So in this case, we are establishing a serial connection, which is just what lets us communicate to the laptop from the Arduino. In this case, we're just saying what type of communication started and what the speed is. Again, you can look up all of these terms for details, but this is very common in a lot of Arduino programs. Next up is the loop, and the loop is the code that just keeps running until you turn the thing off. So this just goes over and over and over and over again. So in this case, we're telling it, the first thing we want to do is read the voltage on our sensor pin. Now, we had already told it up here that we're going to be reading pin A0. Whenever you are adapting a program, either somebody else's or a code from earlier, make sure that the pins match the physical setup on the board. You might also be wondering why we don't just have A0 here. In general, because you can refer to a pin multiple times, if you make changes to your program, instead of hunting down every instance of A0, you know that you'd only have to change it once up here for that change to be propagated down elsewhere. Okay, so we say we read in a value from the analog pin. For Arduinos, it doesn't give us a number 0 to 5. It gives us a number 0 to 1023, where this represents the maximum voltage of the microcontroller, which is in this case 5. So we're reading that number in, and then we actually want to convert that to voltage. So we find out what fraction of the total it is. So that would give us, for example, 0.5 for 50, if it's 50% of the total, about 0.25 if it was a quarter of the value, etc. And we multiply that by the logic voltage, which is the fraction of the total voltage it's expecting. So in this case, 5 volts. So again, if it were half of 5 volts, or 2.5, it would read that as half of the maximum. We'd multiply that by 5 to get back to 2.5. And then these are the commands to print the information to the screen. So in this case, we have voltage as text in double quotes, just so we have a label for the data. And then we print the variable measured voltage, which is where we were storing that number between 0 and 5. And then note here we have print line. The difference between print line and print is that it essentially gives a carriage return or hits enter so that we have a new line each time. And then we have a small delay, in this case a fifth of a second, just so we're not overwhelming the system. This is very common to have in systems like this. So let's check it out and see how it goes. The program is now running, so let's look at the serial monitor. And we see that currently, while this is unflexed, the voltage is 3.87 volts. And as I bend this back, we see that the voltage is increasing. It looks like it goes up to about 4.7. So unflexed, it was about 3.8 something. And then as we flexed it, it went up to, oh, there we go, into the 4.7s. We'll now compare Arduino, which I moved to the left, to CircuitPython on the right. So the first thing to note is that in CircuitPython, there are more import statements than we needed in Arduino. Part of that is because Arduino was designed specifically to work with hardware, while CircuitPython is a variant of the more general Python language. Below that, we have our declarations. In both cases, the first thing I'm doing is telling it that the pin we're going to be looking at is A0. You'll note in CircuitPython, this is definitely longer than Arduino, although later we'll see it ends up saving some space in the long run. So Another thing to note is that if this looks like a lot to remember, one, you'll get used to it, and two, is that in the Mute editor, we have this nice autocomplete feature. So we're going to be using analog inputs. So we would use analog IO, hit period, analog in, since we're reading in the value, and then we specify the pin. One thing that we need to remember here is that in CircuitPython, when you're referring to a pin, you have to proceed with board, dot, and then the pin. That is sometimes a little bit tricky to remember. Next, in both cases, we have our declarations and initialization. Now, in Python, you do not need to specify whether or not it's an int or a float. Based on the value that you are giving it, it will adjust the type accordingly. This also means that if we don't need to declare the type, there's no declarations needed, so we can actually just get rid of these. So pin value equals 0 and measured voltage equals 0. We don't need that in Python. Instead of having to declare it first, including the type, Python says, oh, I am creating a variable called measured voltage. Great, and it just does it on the fly. For logic voltage, we're going to use 3.3 because this board runs off 3.3 volts rather than 5. Other than that, basic idea is still the same, where we have our declarations, although definitely less is needed in this case. Another difference is that we don't need to begin a serial connection. That's handled automatically, so that's something that we can drop. So we don't need any setup loop. In CircuitPython, we would just have that code here, anything that would run at the beginning. Now, there is still a loop structure. In Arduino, it's just a function called loop. In CircuitPython, we don't have a separate function for it. We just say while true. So this is a while statement that will run forever. So it acts the same as the loop statement that we have in Arduino. So now if we look at the code, we have the program reading in the value of the input. Again, the ranges are a little different. Here, the numbers go from 0 to 65,535, as opposed to 1,023 for Arduino here. This statement is shorter than what we had in Arduino because we took care of that work up here. Now, in this case, this isn't actually saving us any space or readability, so we can just ditch that and have that directly in there. Over here, this looked a little unwieldy having this line here, over here, so we had a separate variable for it, but in CircuitPython, there's no need. And then we just print the voltage, our label, and then the actual voltage value. In CircuitPython, one thing to note is that whenever you finish a print line, it then starts a new line automatically. So anything that you want to go in one line, you would just separate with commas, and you don't need to have like a println, for example, that you would need for Arduino. And then for sleep, the main difference is that here it is in seconds, not milliseconds. So 0.2 seconds would just be 0.2 and not 200, for example. Now we'll go back to our physical setup. Let's minimize Arduino and bring back up the actual sensor. So if we look at the serial values, we'll see that we're getting a voltage level while it's straight of 2.54 volts. And then as I flex this back, we'll see the voltage level increasing up to about 3.1. Now, if we compare it to Arduino, we'll note that as we flexed in both cases, the voltage value went up, but they're different voltage values. This is because the voltage value itself depends on, if we look in here, the logic voltage. It also depends on the resistor that we're using as our pull-up. So if we look just at the voltage, it doesn't just tell us about the sensor, it's also telling us about the rest of our setup, the resistors, the type of board, etc. That's not that helpful if we want to look between different setups or really be able to quantify what's happening with the sensor. What we'd like to know is what's happening just inside the sensor. And this is where the work that we did last time, looking at voltage divider circuits, is going to pay off. That way we'll be able to see what the resistance is here for the device so that we can relate to what's actually happening just here and not so much in our external setup. Let's briefly return to our analysis from last time. So we have the voltage divider circuit. Just to remind you that we had the input pin connected to the output pin with a resistor R1 between the two. And then we had that output pin connected to ground with a second resistor, R2. And we saw that the voltage depended on this formula, essentially the ratio of the resistance of R2 over the total multiplied by the input voltage. We can also solve for the resistances if we had, for example, R2 and the voltage readings, but we wanted to find what R1 was, we would just then solve for R1. And likewise, we can do something similar for R2. Now, let's suppose our sensor is at position R1. We know R2, that would be a fixed value that we put in the breadboard. In that case, that resistor, because it connects ground to the output pin that we're reading the voltage of, that's what pulls the voltage down towards 0. And so in this case, where your sensor is at R1, we usually refer to R2 as a pull down resistor. And so our sensor reading would be the resistance of the sensor would be the resistance of the pull down resistor multiplied by the difference between the input and the output voltage divided by the output voltage. Similarly, if the sensor was at R2 and we had a known resistor to R1, R1 would be called a pull up resistor because it's connected to Vin, and so that is what pulls up the V out reading towards the input voltage. So in that case, our sensor resistance would be given by the resistance of the pull up resistor multiplied by the measured voltage divided by the difference between the input and the measured voltage at the analog pin. So we'll now return to our flex sensor. So we'll note that the sensor is in the second position between V out / the input pin and ground, and so it's in position R2, and that the resistor that it's paired with is therefore a pull up resistor because it's connected to the voltage that is coming in. So in this case, that means that we're going to be using this bottom equation here. So the resistance of the sensor is a function of the pull up resistor and our voltage in and our readings. Note that what we're solving for here, the resistance of the sensor, is a property of just that sensor. The way the sensor works actually is that the flex sensor has a conductive material, and as you bend it, the material starts separating a bit, and that separation reduces the conductivity, which has the effect of raising the resistance. But the important thing to note here is that, again, this is a property of the sensor itself, and once we have that value, it's then fair to compare to values that we might have in different setups. We're now just talking about values that are appropriate for the sensor and are not setup dependent. So let's try to get that into our code. We'll move this off to the side to keep that smaller. We don't need the serial to be running at the moment. Okay, so first thing we'll want to do is specify the pull-up resistor that we are using. In this case, we're using a 10 kilo ohm resistor here. So great. And then we would like to recreate this formula. So we would have that our, call it sensor resistance equals pull up times our V out. Now again, that's our actual measured voltage. So we would just use measured voltage here. Great. Divided by the difference between the input voltage, which is to say our logic voltage, minus measured voltage. Sorry, it's a little long. So let's just compare. So our pull up, great. Measured voltage, which is V out, great. Divided by the difference between the input voltage, 3.3 volts, minus the measured. So that is now the sensor resistance. We'd like to be able to print that out as well. That might actually be more helpful. So for now, we'll just comment that out. And we'll have our sensor resistance here. And that'll autocomplete for us. So now we can test it out and we'll see if it does what we expect it to do. We will save that file and let's bring up the flex sensor. So we'll minimize that. So we now have the flex sensor in view. So if we bring up the serial monitor, we see that in the rest position, the resistance is about 34,000 ohms. What we had expected was, as we flex this, the conductive material starts separating, so it's harder for current to flow. So we're expecting the resistance to increase as we flex it. And we, in fact, see that that's the case. So right now, it looks to be about 90 or so degrees. and the resistance has gone up to, it went up to about 90 to 100,000. And then if I let go, again, it starts going back to 35. Now, the important thing to note is that this value is a property of the sensor itself. We needed the information about the pull-up resistor and the system, the voltage, in order to calculate that, but the number we're now getting is only a property of the sensor. So if we use the sensor in different setups, we should still get a similar range of resistances. So now for the first time, we really have a reading about the sensor itself and not just the voltage being read in. Just to briefly show how that could be done, I did kind of a rough version of that here. There are other sensors that have a much more definite response that we'll get to in just a little bit, but just to give an idea of this. So things that I've added the minimum resistance. This is at the rest position. I gave it the maximum resistance, which about 90 degrees is about 95,000 ohms. And I'm saying the angle range is 90 degrees. So the angle will be something between 0 and 90 in this range of resistance. Again, this is fairly informal, but it'll get the idea across. The next part that I've added is a function for the angle itself. So what I'm doing is I'm taking the actual sensor resistance, and however much that is above the minimum, and I'm comparing that to how much bigger the maximum value is above the minimum. So this would essentially say if I had a number halfway in between 33,000 and 95,000, this ratio would be 1/2. And I then multiply that by the angle range. So in this case, the angle range is 90 degrees. If I were flexed 45 degrees, I should be about halfway through that range, multiplied by 90 degrees, so I should get 45. So let's bring the sensor back into view. And if I look at the serial monitor, so this is currently at rest, the angle is about 1.5, 1.8 degrees, so very, very small. And then as I flex this, we're seeing the angle is increasing. And as I get that to about 90 degrees, it looks like, we see the angle values are, again, they're a little wobbly, but let's say it's about 90, fairly close. But in any case, it is able to register with quite a bit of noise, unfortunately, that the sensor is being moved from a small angle up to a large angle. Again, some sensors are much more precise. This one is definitely more qualitative. I'd like to show these principles applied to another sensor, in this case a photocell. This is a sensor where the resistance decreases as the amount of light around it increases. So for any sensor, you're likely to find a variety of different tutorials on different websites, and you'll notice that some might have the sensor paired with a pull down resistor, some with the pull up resistor. The resistor values they have might be different. And so in that case, if you relied on tutorials like that, you are dependent on having exactly what they have and having to really change your configurations, change your code route, etc. So what I'm hoping is that by spending this extra time on the voltage divider circuit, we can see that we don't actually need to have exactly the same pieces they do. So for example, in this tutorial, they have the sensor in the place of R1, and they have a pull down resistor. Versus our case, all I've done is swap the flex sensor with the photosensor, and so this is set up with a pull up resistor. So it doesn't really match what this tutorial has, but that's not really going to be a big deal. So if we look at this case here, so this is their table in the case of the sensor with a 1 kilo ohm pull down resistor. Currently we have a 10 kilo ohm pull up resistor. And so if you rely on just voltage readings, again, you have to have the exact same setup that they do. But we're independent of that now. We can just get the resistance of the sensor itself. And so this side we don't particularly care about. All we want to look at is noting that in a dark room, the resistance of the sensor is going to be about 10 kilo ohms. And in a bright room, it's going to be about 1.5 kilo ohms. So let's remember that. 10 or more is going to be dark, and around 1.5 is going to be a bright room. All right, so let's go back to our code and let's bring the light sensor back into view. Okay, so we're going to save that code and run it. In this case, I have turned on the plotter as well, just so we can get a graph view of that. So right now we can see the resistance here is between 1 and 2000. So if we look at our view, just remember that 1.5 kiloohms or 1500 ohms corresponds to a bright room. So right now there's nothing obstructing it and I actually have a light pointing directly at it. Now if I put my hand over the sensor, we'll see that the resistance goes up. If I lower it even further, we'll see it getting darker and darker and darker. And right now, with my hand directly on top of it, blocking most of the light, we're seeing it definitely qualifies as a dark room. Again, take my hand off. It then is going to drop down back into light room territory, somewhere in between. So really, this shows the difference between analog and a digital sensor. Analog sensors have a range of values, but in this case, we're able to see that even though we have a different setup and a different resistor, that we're still able to get the same information because we can directly read the resistance based on the analysis that we've done and not rely on any particular setup. A couple things that I would like to note though. One, you don't want to just use any resistor. If you have a resistor that is too low compared to the range of values that you would expect from your sensor, or too high, you run the risk of the ratio between R1 and R2 either being too close to zero or too close to infinity. And essentially that can lead to some problems where it's really hard to get detailed information from the formulas. This is less of an issue with the microcontrollers that run Circuit Python because if we go back to the code here, turn off the plotter, we'll see that it's much more fine-grained. Recall in the Arduino, it only takes values from 0 to 1023, while this goes to more than 65,000. So this does have more detail, but you still want a resistor that is within the range of values that you would expect. So here, inside of a room, I would expect a value between, well, about here and here. And so having a 10 kilo ohm resistor is appropriate. On the other hand, if this brightness sensor were outside and I'm expecting a range of values from 300 ohms to 100 ohms because it's in daylight, then I would want a resistor, probably a 220 ohm resistor within that range. So you can't use anything, but it does give you a lot more flexibility because as long as you're somewhere ballpark, you'll be able to take care of it. So this approach works for a bunch of other sensors, basically anything where the value is based on the resistance. Thermistors are a type of temperature sensor. There's a variety of other things that work on this principle. I don't want to go through all of them. I'll leave that for you to explore as you come across them in class. But again, just to show that this method really does work in a variety of situations. Now, there are other types of sensors that are voltage dividers, but have all of that in the internals of the sensor itself. So one of them is a potentiometer, which is a fancy way of saying basically a control knob. And the way it works is that inside there's a band of resistant material, and you attach one end to VIN and the other to ground, and then the knob controls what's called a wiper, just a thin piece of conductive material that then touches the resistive material here. So what that means is if I have current flowing through here, it will move along this amount of resistive material and then hit the wiper to V out. So basically, if I have the knob turned this direction, there's very little resistance between V in and the pin that we're reading, but a lot of resistance between our pin that we're reading in and ground. In other words, in this position, R1 is very small, while R2 is very large. On the other hand, if we were to turn the knob this way, there's more resistive material to go to now to connect the pin that we're reading with RVN. So that would make R1 very large and R2 very small. We can see the effect that this would have on the voltage. So in the case of R1 being very small, well, intuitively, then there's much less resistance between VN and the input pin than there is between the pin here and ground. So we'd expect these voltages to be more closely linked, and that would be the case. So we're expecting a high voltage in this case, versus here, there's a lot more resistance between VN and the pin that we're reading than there is versus ground. So we expect the voltage to be pulled more closely down to zero, and that is also verified by the math. So if we look at this, we'd see that, well, this number essentially, R1 R2 divided by R1 plus R2. If we were to move that to one side, we would have that V out divided by V in is this ratio. But if we look at the diagram, this is saying the ratio of the voltage we're measuring to the input equals R2 divided by R1 plus R2. So if R2 is this resistance here between ground and the input pin, well, and this is R1, that means R1 plus R2 is just this total range. So the ratio R2 divided by R1 plus R2 is exactly what fraction of the range of motion the knob is at. So if this is all the way at this end, it would be 100%, and so that would make the ratio 1, and so V out would equal V in. If this were turned all the way to the other direction, then that would be at 0%. If it were halfway, then if it's halfway, we would have R2 would be half of R1 plus R2, and so you would get 50%. So what this works out to is that, again, this ratio of V out divided by V in is precisely the percentage of the range that it's been moved. If it's a quarter of the way, halfway, 3/4 of the way, or 100% of the way. So this gives us a really easy way to see what the position of the knob is. So I've cut out some of the code that we didn't really need anymore for this part. So what we were just mentioning was that we needed the ratio of the V out over V in, or in other words, the measured voltage divided by the input voltage or logic voltage. We actually have that right here. It's the pin value divided by 65,535. If that doesn't jump out at you, then think about it. But just to make things a little more clear, we'll create a new variable called position, and we'll set it equal to the measured voltage divided by the logic voltage. Okay, so, one last thing, since this is going to be a fraction of the total, we want a percentage, so we'll multiply that by 100. All right, so then if we run that, and let's bring up the plotter, hit save. Okay, so right now the knob is pretty close to being in the middle. So now if I rotate this, we see the voltage climbing up. Keep turning it, I take it up to the end of its motion, and that is actually really nicely over at 100%. There's a really small arrow that is the end of the range of motion, but yeah, right up at 100%. So that is perfect. So if I bring that back down to pointing pretty close to straight down, that should be fairly close to being in the middle. And if we look at the voltage, it's pretty close to 50. And then if I turn this completely the other direction, we see that number go down very close to 0. We could bring up the serial plotter, and it's 0.25%. It's a really low number. So we get a number very close to 0. At one end, we get a number that is close to 50% right in the middle, and then a number that's really close to 100% right up top. So that's great. Now, I don't want to give the impression that every analog sensor works in the voltage divider principle. Sometimes they do a little bit of the work for you, which is really nice. So one of these is the TMP36 temperature sensor, and the pinouts are right there. And if we look at the breadboard, it's pretty easy to set up. So the nice thing about this is that it doesn't really matter what the input voltage is. So as long as it's in this range, you're good to go. The analog voltage that it gives the microcontroller isn't based on that input voltage. It will give you the voltage in a specific range as long as you're give it adequate voltage. It puts out the same regardless if you're feeding it 5 volts or 3.3 volts. So in this case, they give you the formula for the temperature in Celsius. So regardless of which microcontroller you're using, this formula should be valid. So if you look at the code in Circuit Python, I'm taking the V out, I'm putting it in millivolts as it's specifying, subtracting 500 and dividing by 10. Again, they're just providing that formula, so that's really nice. And because I'm not as familiar with Celsius as far as getting a sense of how accurate that is, I'm also converting it to Fahrenheit. So if we save this program and run it, So currently it is saying that the temperature in the room is 25 degrees Celsius or about 77 degrees Fahrenheit. Currently my air conditioning is set to 75, so that seems accurate, especially because there are lights shooting on it, and also it's near the microcontroller, which is generating some heat, so 77 degrees seems very accurate. And now, just to check to see that it's able to change, if I instead look at the plotter view, so it's plotting both the temperature in Celsius in green and Fahrenheit in blue. If I then put my finger on the temperature sensor, I would expect those to start climbing up, and indeed they do. And then if I let go, it should then start slowly going back down. So in any case, so this is an example where you don't need to worry about the voltage divider logic. They just give you an explicit formula. Everything is internal to the device. And on the instances that that happens, that is really easy to use. But it isn't always the case, but I did want to give an example of such a sensor. That will be it for this video. To summarize, we used the analysis that we did last time on voltage divider circuits in order to give us a unified overview of a few different sensors. These included a flex sensor, a brightness sensor, and a potentiometer. And by doing this, instead of relying on having one particular resistor or tutorial, we were able to use essentially the same program with a few variations and the analysis that we did in order to find out what the resistance and hence value was of the sensor itself in a way that was independent of the particular microcontroller or resistor that we were using. In addition, we talked about the TMP36 temperature sensor as an example of an analog sensor that isn't resistance-based, but which still uses the analog inputs in order to give us a value that we're looking for. So that'll be it, and thanks a lot.